Question is, figure shows a finite energy signal phi t. First part is we have to sketch the impulse response of optimum filter that is matched to phi t. And second part is determine the value of output of match filter at t equals to capital T, assuming noise is 0 and input is phi t. So here the energy signal phi t is given, which has some finite energy, and in the first part we have to find optimum impulse response matched to phi t. According to the question, the duration of phi t signal, that is called energy signal, is capital T second, and outside this interval the value of phi t is 0. Now for match filter, the optimum impulse response is equals to phi function of capital T minus small t, that is time reverse and delay version of input signal phi t. So the optimum impulse response can be determined using phi capital T minus small t. Here phi t is given, which having a finite energy within interval 0 to capital T. First we take time reversal and function becomes phi minus t, having duration from minus t to 0. After time reversal, we take time shifting. Here in case of negative time, plus t represents a time delay. So we shift phi minus t to the right side by capital T. So from here we find that the given signal phi t is identical with the phi function minus t plus capital T. And this is the optimum impulse response of the match filter, that is matched to phi t. And the second part is we have to determine the value of output of the match filter at t equals to capital T, assuming noise is 0 and input is phi t. For this we consider an optimum filter having impulse response ht with input phi t, and we know that output of optimum filter is simply the convolution of input signal and impulse response. So yt is equals to ht convolution phi t. And in the first part we have determined optimum impulse response ht having value a between 0 to capital T and 0 otherwise. And this optimum impulse response is identical to input signal phi t. So both are same. Now we have to determine the output signal yt, that is a convolution of ht and phi t. So we first consider case 1, when small t is greater than 0 but less than or equals to capital T. Here phi t and impulse response of optimum filter ht is identical, having value a between interval 0 to capital T. And we know that output yt equals to ht convolution phi t, and its formula is integration h tau phi t minus tau d tau, taking limit tau equals to 0 to infinity. So in convolution formula we have to multiply h tau with phi t minus small tau. Now first we write phi minus tau, that is a time reversal, and simply put t equals to minus tau. After time reversal we make time shifting. Here plus t represents delay in time, so we move phi minus t towards right side by small t. Here we consider a case small t is greater than 0 but less than or equals to capital T. After representing phi t minus tau, we take h tau. So here h optimum tau is simply a function having value a between 0 to capital T. Now, after representing phi minus tau plus t and h optimum tau, we put it in formula. After multiplying, we find a common region between 0 to small t. And we know that the value of phi minus tau plus t is a and h optimum tau is a. So our integration becomes 0 to t a square d tau. After solving, we get output yt equals to a square t. And this is for the case when t is less than or equals to capital T. Now we consider second case. Here small t is greater than capital T but less than or equals to twice of capital T. In this case, we again consider phi minus tau plus t such that the value of small t is greater than capital T but less than or equals to twice of capital T. That is represented by phi minus tau plus t. Accordingly, the output yt is equals to h optimum t convolution phi t. So we simply write the formula, that is integration h tau phi t minus tau d tau. In this case, the range of optimum impulse response h tau is 0 to capital T, but the limit of phi t minus small tau is from minus capital T plus small t to small t. So here we find a common region. This common region having interval between minus capital T plus small t to capital T only. After taking this common region, the output yt equals to integration of a square d tau taking limit minus capital T plus small t up to capital T. And after solving, we get output yt equals to a square within bracket 2 capital T minus small t. This is a case when we take small t greater than capital T but less than or equals to twice of capital T. Now we combine both cases and we get output yt 0 for t less than 0, a square t for t greater than 0 less than or equals to capital T, and a square to capital T minus small t for t greater than capital T but less than or equals to twice of capital T, and 0 otherwise. And graphically, the output yt is shown in figure. Here, for t less than 0, the value of yt is 0. Between 0 to capital T, the response is a square small t, that is the ramp signal. Also for interval capital T to twice of capital T, we have a square to capital T minus small t. Here, at t equals to capital T, we get a square capital T. Also, using third result, at capital T, the value is a square capital T. So accordingly, we conclude that the match filter is implemented using a circuit known as integrate and dumped circuit. Here, integrator is used to get ramp signal. Here the input is rectangular pulse denoted by phi t After integrate, we get yt, that is shown in figure. Here, the integrator computes area under the rectangular pulse, that is A capital T. After sampling at t equals to capital T, the integrator immediately stores its initial condition, that is between intervals 0 to capital T, hence called a dumped circuit. So the mesh filter can be simply implemented using integrate plus dump circuit. So the output of the mesh filter y0 t equals to a squared t for interval t greater than 0 but less than or equals to capital T.